In this lesson, we shall focus on applied mathematics, right? We shall be focusing on the power method. Power method. And we begin as follows. Right. To conclude the discussion we started last time on the power method, it was the most comprehensive coverage of this section on the power method. I must indicate that it is already this is what you need to expect to see. Okay, in your final assessment. But now, at this point, if we are looking at question one and you consider the eigenvalue problem, right? Ax equals lambda x, A equals the matrix given, and its inverse, the inverse of the matrix A is as given. Use the power method to estimate the remaining eigenvalue and the associated eigenvector. All cases start with the vector 1, 1, and 1 and iterate 3 times. Use at least 4 decimal digits with rounding. So now, we will remember last time that we looked at one case where we looked at the largest, right? The largest eigenvalue. We looked at the smallest eigenvalue. But smallest how? Smallest in terms of the magnitude. But today we are going to look at the intermediate eigenvalue in terms of magnitude. And we're then saying the remaining eigenvalue and associated, so we need to use the power method to estimate the remaining eigenvalue because the 3 by 3 matrix actually, we saw, it actually has a lambda 1, lambda 2, and lambda 3 as its associated eigenvalues. But now the question we're asking, therefore, is how do we handle? We saw how we deal with the most dominant. How did you deal with the dominant one? To deal with the dominant one, the strategy is to make sure that you always factorize the largest value from the matrices when you do the matrix multiplication. Right, you always factor out the largest value. But for the smallest one, you take the inverse, use the matrix. We used the matrix A last time, and we factored out the largest entry in the associated vector, like we did last time, for the inverse. But now for the inverse produces deals with the smallest eigenvalue. And the question that remains is the most pivotal question. How do we deal with D? How? How do we deal with D? So now we will actually then recall something here. Okay, there are a couple of things that obviously we need to take into account in the way we actually have discussed this. There is a lambda 1, which is minus 4, 3, and 9. Okay, these become what you call the eigenvalues of the matrix A. We did them last time. Normally, they won't ask you to find them. They won't ask you, they'll not ask you to find the eigenvalues, but they will ask you to use the power method to estimate because that is what this module is about. So now let us deal with the remaining case. So we dealt with the smallest one because the smallest one is this one in terms of the magnitude. And we dealt with the largest, which is 9 in terms of the magnitude. And then now we have the intermediate one. Intermediate one. Okay, good. Right, so let us deal with the intermediate one. We start as follows and say that the two calculated eigenvalues, we did lambda 1 last time, and this continues from what we did last time, and we got approximately 9 point. Right, we got approximately 9.2667. And Lambda 1 and lambda 2. 2.4. Okay. Right, so these were the two. But in both cases we did last time, you remember that this 2.4 is close to the smallest one. It's close to 3. And the 9.2667 was actually the one close to 9 when we did the estimate. We need to find the one that is close to -4 right now. Right, so in any case, now these two were done last time, and this continues from where we left off, but both lie in the union. Right, lie in the union of the most famous of the disks. Right, I want to say that these are not just ordinary disks; they are special disks. We called the Jeshgorin disks. Right, the Jeshgorin disks. D1, D2. The Jeshgorin disks. In the union of the disks, D2 and D3. We saw this last time. Well, once again, this is a continuation, but we know that these eigenvalues, they lie in a given disk. An eigenvalue lies in a disk, or the eigenvalues, if there are two of them, they can always lie in a union of disks. So now we then say these two we saw last time, they both lie in the union of the Jeshgorin disks, D2 and D3, right, as we did last time, but today we shall look at the third one. Right, hence we know. Okay, because this one is already there in your assessment. We know from the first Roman figure, you're going to make this one in a few days. We know from the first Roman figure that the remaining, okay, the remaining is the most technical, is the most difficult. All right, so is the remaining eigenvalue lambda 3, because we did the first two, lambda 1, lambda 2, but now lambda 3 must lie. Right, must lie in disk 1, just go in disk 1. Right, so with this mentioned, that is to say, specifically, the third lambda 3, must be near. Right, must be near right, so this is it. Right. So we actually therefore investigate the following. Okay, just to pause there to reason something very, very important in this case. We pause to reason this very carefully. So now, once again, we are then saying, what were the centers of these disks? Right, we actually dealt with the disks last time, and we're able to see that the centers of the disks are these things here, are these entries that lie on the main diagonal. Because, for example, we actually were able to make the following realization. If one remembers very well, that the disk 1 contains Z in the complexes, such that you have Z minus 6 is less or equal to the off-diagonal entries in the first row, which will be 0, modulus of 0, modulus of 6, and this would be 6. That became the first disk. The second disk, you can put it here, contained Z in C, such that we then have Z minus 9, because 9 is this one. And it is therefore less or equal to the off-diagonal entries in the same row, modulus of 4 plus modulus of 2, and this is 6. Disk 3, which is Z minus 5, which is less or equal to the modulus of minus 3, the modulus of 0, which is 3. Okay, now we continue now with this. And so with this in mind, I want us to continue to interpret these specific notions, but very, very carefully. Right, extremely carefully. Right, so now we're then saying that the remaining eigenvalue, that's what we're saying here, and hence we know from Roman figure 1 that the remaining eigenvalue lambda 3 must be in D1. I still want to go back to this a little bit. Okay, we did this last time, but I want to speak about the disks. So that you can be able to make sense of this very well. The general definition of a Jacobian disk is that the disk I, for example, is given by the Z in the complex numbers, such that you have Z minus AII is less or equal to N, which is J equals 1, J not I. And then it is like this. 1, 2, and so on. Okay, this is the general definition of the Jacobian disk. And then we have that. Okay, let us reflect on what on the disks, the Jacobian disks. Let us reflect on what we call the Jacobian. Right. Jacobian disks. Right, so now we have the imaginary Z, and then we have real Z. Now, we'd have that in this case, we have this here horizontal, like this. Now, let's look at disk 1. It's going to have center minus 6. And then it's going to be like this. It's going to actually be, because it is of radius 6. Center is minus 6, and then the radius is this number 6. And then obviously we're going to shade it because it's less or equal to, the fact that it is less or equal to, and all these the Jacobian disks are less than or equal to, so we'd have the interior that we are focusing on. Now, there are other disks like the disk 2, because there are 1, 2, 3 main diagonal entries. So we'd have, for instance, the 5. Disk 3 is going to be 5. Then it's going to be 3 units. So now 3 units radius. So you're going to say 5 minus 3 giving 2. 3, you get 8. Right, so you have this. And then right now, disk 2, you have center 9. Right, there's center 9 and then radius 6. So if you then say 9 minus, right, so center 9 and radius 6. So if the center is 9 and then now you need to measure 6. So you have 9 and then you're going to subtract exactly the following. Yeah, you'd accept. So let us focus on disk number 2. Right, so disk number 2 becomes a disk as follows. So it's going to have center 9, but its radius is 6 units. Right, so if its radius is 6 units, you're going to have, for example, 9, and then you subtract 6 from it. Right, because that's what you're going to have. The center is 9, and we have 4 plus 2, which gives you exactly a 6 there. Right, so at this pointer, you would have a center 9. The radius is 6, so you actually would go 9 minus the 6, giving you a 3. Okay, so, and then now you add also 9, radius 6, you add, that is going to be about 15. Something like that. Something like so. Okay, so at this point, you've then been in a position to then realize that you have certain disks. And the disks are, for instance, as follows. So you're going to have, okay, I wanted to say here, check this out. So this one here is going to be, it's going to be 5, but 5 radius 3. So 5 plus 3 is going to give you 8. That's what we meant. So 8 is going to be close to 9. So the center is 5, but the radius is 3. So you add 3 plus 5 plus 3 gives you 8. And then 5 minus 3 gives you that. So yeah, wanted to draw this disk like so. Okay, so that these disks overlap like they did last time. And now we remember their 2 theorems. Right, and the main significant theorem is the following theorem that you're going to recite again and then we shall move on. Right, which is theorem 2 of these Jeshgorin disks. So if K of these disks do not touch the other, n minus k disks, then exactly k eigenvalues. Right, then k eigenvalues counting multiplicities lie in the union of those k disks k disks. Okay, we reiterate the statement we have just written, theorem 2, which is the most significant one of the Chebyshev disks, because we're going to be using these. This is a very intense review of the average, because now we dealt with the smallest and the largest, but what to do with the intermediate one, the average eigenvalue. So we need to be very concise, and the way to do it is to ensure that we have our supporting theorems stated clearly. If k of these disks do not touch the other n minus k disks, right? Then exactly, right? So we then say, then exactly k eigenvalues counting multiplicities lie in the union of those k disks, right? So at this point, we have three eigenvalues because there are three main diagonal entries, 1, 2, 3. So, and hence we have the three disks. Now, I want us to remember what we did last time, but also look at where these eigenvalues are going to be. Now, there is an eigenvalue. What are the eigenvalues? So we did one eigenvalue was exactly a -4. The other one was 3, and the other one was 9. Like so. These were the eigenvalues we did for the matrix A. Now, -4 is the number that sits somewhere here. That puts lambda equals -4 in this disk. And then there is lambda equals 3. Now, where is lambda equals 3? Where exactly is lambda equals 3? Because this one is a okay, we're gonna work it out very carefully, because it is such that that is the disk with center 9. So the disk with center 9, this one, disk 2 with center 9 is radius 6. So if you have 9 minus 6, you get a 3. Okay, so we have the following. Okay, so now if we then are looking at the lambda equals 3, then it's going to be here. So it is in the union of these disks. It is in the union of the disks. Now, you then have also the lambda. So now we have lambda equals 3. And then we also have lambda equals what? Lambda equals 9, which is this one. So the lambda equals 3 and the 9 are obviously in these disks, in the union of the disks. In which case we dealt with the smallest and the biggest one. 3 is the smallest in magnitude terms, and also 9 is the largest in magnitude terms among the eigenvalues that are here. But now I want us to then, obviously it's not, we have more than this, because we need to shade the interior of this disk. Why do we shade the interior? Because each of the disks is defined as a circle less than or equal to, meaning we consider equal to is the boundary, the less than part becomes the interior of the disk. Now, we continue with our analysis of this here. We continue with our analysis of this here. We take a look at the next little problem. And so, with this mentioned, okay, we have something concrete to say about the following assertion we need to make here. Right, there's an assertion we need to make, but it will be backed by the Chebyshev theorems. To say, hence we know from Roman figure 1 that the remaining eigenvalue lambda 3 must lie in disk 1. Yes, we can see clearly that the lambda equals -4 must lie in disk 1. And these are the other two. So we can see -4 lies in disk 1. And the lambda 3, lambda equals 3, lambda equals 9, they lie in the other two disks. Okay, so that is sorted. Right. And that is to say, right, that is to say, lambda 3 must be near minus 6. Lambda 3 must be near minus 6. Okay, because why minus 6? Minus 6 is the center. So it must be close to minus 6, the center of these disks, or of the disk 1. Okay, so right. Now, I feel like I need to state theorem 1 very quickly, just to make sure that there's a balance even on this recording and everything can make sense. Please, sir, allow me in a split second to state theorem 1 of Jeshgorin. And the theorem 1 actually asserts that you let A, B, an n by n matrix with the AIJs real or complex valued. Right. So we then say, then all the right. Okay, we are here. Right. Okay, we continue, please. We continue. Okay, we continue. Then all the eigenvalues of A lie in the union of the following. N disks. N disks. D subscript I in the complex. In the complex plane. Right. So that we have with us the D I Z and C Z minus AII, which is less or equal to J equals 1, J not I, AIJ, I12, and so on. So that in the end, the DI is simply, right, the DI is simply, okay, I'm just stating this, just quoting theorem 1, because so that we can make sense of everything quite on this recording. So DI is simply the disk, right? It's simply the disk with center AII and radius, right? And radius equal to the sum to the sum of the absolute values of the absolute values of the entries in row I, right, which are not, which are not, right, which are not on the main diagonal, on the main diagonal, on the main diagonal, on the main diagonal, right, 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 right. So this is what we have exactly. This is what we have precisely here. This is what we have precisely. So now at this point, we reiterate this theorem one. Let A be an n by n matrix with the aij's real or complex valued. Then all the eigenvalues of A lie in the union of the following n disks. Right. Right. So now if you let A be an n by n matrix with the aij's real or complex valued, so the entries inside the matrix, because they are A11, A12, A13, A21, A22, A23, A31, A32, A33. Those are the entries, and we call them the aij entries. So if let A be an n by n matrix with the aij's real or complex value, then all the eigenvalues of A lie in the union of the following n disks. Di in the complex plane. And Di is exactly these. Right. So if you have a matrix, then all, but no exception, like all of them, the eigenvalues of that matrix will always lie in the union of the following disks. And this is Chebyshev theorem 1. So if you have a matrix, then there's no way these eigenvalues cannot be in the union of the disks. Now, we are then saying here, lambda equals -4 lies in the first disk, and the other two values lie in the other two eigenvalues, they lie in the union of the other two disks. Okay. And we have stated clearly that we know from Roman figure 1 that the remaining eigenvalue lambda 3 must lie in disk 1. That is, lambda 3 must be near -6. Must be near -6. Because if lambda 3, and by lambda 3 we mean the -4, because this is sort of the 1, 2. So the lambda 3 is the -4. It must therefore obviously lie in the -6. Right, in the -6. -6. Okay. So we then continue with our analysis here. And then we then say, this lambda 3 must lie near minus 6. So we continue now with our analysis of this, and we then say, in order to use the inverse power, the inverse power method, we must, right, we must first, shift. So we perform a shift for the first time ever in the power method. We must first shift the eigenvalues. Must first shift the eigenvalues. If lambda is an eigenvalue, of A with corresponding eigenvector with corresponding eigenvector x. In order to use the inverse power method, okay, so obviously we shall be dealing with the inverse matrix here as well. We must first shift the eigenvalues. For the first time, we did not perform shifts before. We only do shifts when we are dealing with the intermediate eigenvalue, or the eigenvalue whose size or magnitude is intermediate. It's not the smallest or the biggest, but is midway, right? If lambda is an eigenvalue of A with corresponding eigenvector x. So we're dealing with an eigenvalue, lambda, and this eigenvalue lambda is with the corresponding eigenvector x. Okay? Then we have the following. Then we have the following. Then AX is lambda x. Now, this becomes the eigenvalue equation, right? But all the time in mathematics. So we know that AX is always equal to lambda x because it must be close to minus 6, which is the center of the disk. This one here. We're going to then have AX minus 6. This minus 6 here. And then we multiply these by IX. Which means lambda x minus that, which is A plus 6I. A plus 6I. A plus 6I. IX. So we factorize here the IX, and this is what we have. Plus 6I, and then we can just put only an X here. Only X is enough outside. Only X is sufficient. And this is then the same as lambda plus 6 X. We've performed a shift. We have performed a shift. Why have we performed the shift? We performed the shift because we are dealing with an eigenvalue that is intermediate in a 3 by 3 matrix. And we proceed as follows. Henceforth, Hence the eigenvalues. Hence the eigenvalues of A plus 6i are lambda 1 plus 6, lambda 2 plus 6, lambda 3 plus 6. Okay. So now we are dealing with the eigenvalues of the matrix A plus 6i, which is this one, A plus 6i, and we are then saying the eigenvalues are the ones, are the lambda plus 6. So then the eigenvalues are lambda 1 plus 6, lambda 2 plus 6, lambda 3 plus 6. And the eigenvalues of A plus 6i are lambda 1 plus 6. Right, or exactly the following. Exactly the following. They are precisely the following. So we have that. And I was effectively saying here, obviously, as said already, hence the eigenvalues. Hence the eigenvalues of A plus 6i are lambda 1 plus 6, lambda 2 plus 6, lambda 3 plus 6. And the eigenvalues, right, and the eigenvalues of A plus 6i inverse are, so for the inverse, therefore, they become the reciprocals, 1 over lambda 1 plus 6. 1 over lambda 2 plus 6. 1 over lambda 3 plus 6. Right. Note also, note that the eigenvectors remain unchanged. The eigenvectors remain essentially untransformed. Okay, we're dealing with the intermediate eigenvalue in a 3 by 3 matrix. This is sort of the biggest you will meet in the in this module. Right. We did 2 by 2. 2 by 2 are easy because it's only 2 eigenvalues, then the smallest and the biggest. But here you have also intermediate ones. So now, since lambda 3 is near, lambda 3 is near minus 6, the center of disk 1, we're able to see that lambda 3 plus 6, which is associated eigenvalue, will be small. Will be small. Okay? Thus, 1 over lambda 3 plus 6 will be the dominant eigenvalue of A plus 6I compared to 1 over lambda 1 plus 6. Lambda 1 plus 6. Okay. There's the 1 over lambda 3 plus 6 will be small because we dealt with lambda 1, say 3, lambda 2, 9, and then lambda 3 minus 4. So if we deal with 1 over lambda 1 plus 6, which is 3 plus 6, 1 over 9. Okay, we continue. And then we shall have, for instance, 1 over lambda 2 plus 6, which is 1 over, what is lambda 2? It's going to be the 9 plus 6, lambda 2 that. And this is going to be exactly 9 plus 6, 15. 1 over lambda 3 plus 6. Lambda 3 minus 4 plus 6 will be, minus 4 plus 6 is 1/2. So you're able to see that if you look at, we're then saying lambda 3 plus 6 will be small. Okay, because lambda 3 plus 6, lambda 3 is minus 4 plus 6, which is 2. And this one is 9, this one is 15. The lambda 1 plus 6 is 9, the lambda 2 plus 6 is 15, and the lambda 3 plus 6 is 2. So surely lambda 3 plus 6 will be small because 2 is the smallest one. Thus, if you take the reciprocal, it's going to be the biggest one. It's the most dominant. Thus, this one will be the dominant eigenvalue of the inverse matrix compared to 1 over lambda 1 plus 6, which is approximately 0.0655 and 1 over lambda 2 plus 6, which is 0.1190. Okay, let us analyze this. Let us analyze this. So lambda 1 plus 6 would be that one there. Okay, let us analyze this. So if we choose, let us bring a calculator here so that you can practice and make sure we understand this. So we're going to, for example, take, if within 1 over lambda 1 plus 6, if lambda 1 is 3, either we can say lambda 1 is 3 or 9. So let us say it is 3 and then we have 1 out of 9. Right, so 1 out of 9 gives us what? Gives us 0.1 recurring. And then if you do 1 out of 15, right, 1 out of 15. Yeah. So it's going to be not point that. So at this point, what we're able to realize is that if we take lambda 1 to be the 9, so we take, let's measure the order, of course. We take lambda 1 to be 9, lambda 2 to be 3. Okay, you can switch them around. This doesn't really matter. But now you need to, very important to be consistent as we make the choice. So lambda 3 is going to be 2, but now the lambda 2, so this is going to be lambda 2. And it's going to be 3 plus 6, which is 1 over 9, which is 9 plus 6, 15. Thus, the 1 over lambda 3 plus 6 will be the dominant eigenvalue of A plus 6I. Yes. Compared to 1 over lambda 1, which is the 1 over 15, which is this. And then 1 over lambda 2, which is the 1 over 9, which is 0.11. Good. Which is the 1 over 9. Good. Now, what is the meaning of all these things here? The meaning of this is then, and so. And so the power method, which has been much of great delight here, can be used to find it. First, we use the Gauss. First, we use the Gauss-Jordan method. Okay, we use the Gauss-Jordan method that is used in undergrad studies for matrices to find precise solutions to obtain A plus 6I. Okay. Okay. All right. So now at this point, if we then take the associated matrix and we're doing the matrix A plus 6I. So in the matrix A plus 6I, we're going to add 6 along this main diagonal entry. So if you add 6 here, it's going to be minus 6 plus 6, giving a 0. The rest of the other entries are the same. And then here, there's a 4. And then here you add a 6, you get a 15, a 2, a minus 3, a 0. You add a 6, you have 11. 1, 0, 0. 0, 1, 0, 0, 0, 1. So now we want to find the inverse. So to find the inverse of this matrix, we want to find the inverse of this. So the question you're asking is A plus 6I, what is its inverse? If you find the inverse, it is equal to what? This is the shifting method for the power method. At this point, we are able to realize a couple of things. We want to have, for example, a 1, row 2 plus row 3. 1 over 6, row 1. 0, 0, 1. 1 out of 6. And then you have 15. 13, 011. So we have the following. Okay, let's continue. So we got the 1 there, and then now we have -3, 0, 11, 001. And then let us continue with the row reduction process. This matrix is row equivalent to the next one. Here we need a 0. So we can interchange the first and the second rows. 1, 15, 13. 0, 1, 1. Okay. And then here you're going to put 0, 0, 1. Oh, yes. But you need to perform another. So here you can say row 3 plus 3, row 2. Row 3 plus 3, row 2. So if you look at row 3 plus 3, row 2, you have a 0 here. Plus 3, row 2, you have 45. 3, row 2 is 3 by 13, which is exactly at 39, 40, 50. And then you have a 0, 3, row 2, which is 3, and then a 4. So that then in the end, we have the following. Right, so let's do an interchange of the third row and the second one, which is 15, 13, 0, 1, 1, which is 0, 45, 50, 0, 3, 4, 0, 0, 1, 1 out of 6, 0, 0. Okay. So that in the end, row 1 minus 1/3 row 2. So now we have 1/3, and then it's going to become a 0. Okay, so you have 1/3 of this. So you have 50 over 3, which is minus 50 over 3, and then with row 1, 39 over 3, and this becomes exactly minus 11 out of 3. And then 0. Minus 1, and you add, we have a 0. Minus 4 over 3. Plus 3 over 3. Minus 1 over 3. Right, so So it's 1 out of 45, row 2. 0, 1. 50 divided by 45. 10 out of 9. 0. 1 out of 15. 4 out of 45. Like so. So, which is 1, 0 minus 11 out of 3. And then we have 0, 0 minus 1/3. 0, 1, 10 out of 9. 0, 1 out of 15, 4 out of 45. Zero, zero, one. 1/6. 0, 0. Row 1 plus 11 out of 3, row 3. So you would have 11 out of 18, 0. Out of 9, row 3. So in the end, then you have minus 10 out of 9 times 1 out of 6. What is this? 2 goes how many times here? 2 goes 3 times here, 2 goes minus 5 times, and this is minus 5 divided by 3 by 9, 18. Check this out. So if we have exactly that, which is minus 5 over 18. Okay, let us write this one here. And then now if you multiply this one is 1 out of 15. And this one is 4 out of 45. And then this one is right. Right. So we continue. Right, 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 right. Okay. So this is the answer we're getting. But now, obviously, we think and carefully check if this answer is correct before we proceed. So just looking at the inverse matrix here, just in a split second, we're going to confirm the accuracy of this matrix. So in other words, if this is the matrix A, this one, then the inverse is the one we've got. So right. So this is the original matrix A plus 6i. Then the inverse is the one we've got. I'm trying to perform a verification right now just to make sure that we do not proceed with an inverse that has an error in it, because a simple error would be disastrous. Because I mean, in a matrix, a simple error, a single error, I mean, is an entry that is erroneous will cause some trouble. will cause some trouble. So there's an entry that you need to change. Yeah, because the 3 by 9 is 27. See, the 3 by 9 is exactly a 27. So that we have it here. So that is what we have. So that this is the matrix. Right. So now, which is A plus 6I. We find this inverse is 11 out of 18. It is 0 minus 1/3 minus 5 out of 27. 1 out of 15. 4 out of 45. 1 out of 6. 0, 0. Right. So we continue. We continue. So hence that is the inverse of the matrix there. Now, because we performed the shift to find the inverse, now the power method is being used. Now, the power method. Okay, because this one is examinable every year. The power method is applied. It's not that we're just talking about it. In the obviously now we're gonna use, remember, in all cases, but in all cases, no exception, we actually gonna do the following. So we're gonna start with the 1, 1, and 1. So we're gonna have the inverse. Right. 18. Right. Right. So 1 out of 15, 4 out of 45. 0, 0. Which is 11 out of 18. 0 minus 1 out of 3. Minus 5 out of 27. 1 out of 15. 4 out of 45. 1 out of 6. 0. 1 out of 6, 0, and then 0. And then now you're going to have the 1, 1, 1. Why? Because now we have found the inverse of the translated matrix, and then we actually are multiplying by the vector 1, 1, and 1, and iterate 3 times. Use at least 4 decimal digits to do the work. So now if we multiply these, we get the results. Let us practice together. Now to multiply these is something way too straightforward. We use our calculator. Right, so, which is 11 out of 18. 0 minus 1 out of 3. So now we're getting 5 out of 18, and this 5 out of 18 is 0.27 recurring. 0.2777. At least 4 decimal digits, so we're 4 decimals. Okay, and then we practice with the next one. And then now we're going to do row by column multiplication, meaning that we're going to have the negative, then we punch the 5 out of 27. Right, if we punch the 5 out of 27, then we're going to get the following. 1 out of 15. And then we add 4 out of 45. Right, so in the end, then it's not minus 0.0296. 0.0296. Okay, now we're going to multiply the 1 over 6 by 1, 0 by 1, 0 by 1. So which means we have 1 out of 6, which is 0.16. 0.1667. Now we're going to extract the most dominant in terms of magnitude. So 0.2 is the biggest one of 0.02 and 0.1. So we're going to extract 0.0277. And then now in the end, we're going to have what? Then we're going to have, we divide everything. So it's 1 here. You divide this by that. You'd get minus 0.0296. Dividing these by that, you get 0.1667. Right. Right. So 0.1667. We divide by the dominant one, 0.277. 7. And this is if you divide this one, the 0.1667 by the 0.2777, you get approximately 0.6. Yeah. So I'm going to change this one, which is 0.600. And then this one, if you divide, okay, see, I wrote these ones. I need to change it because they're different from this. So now if you divide also by, you divide the minus 0.0296, which is 0.2123. 0.096. Okay. So if you have this, we divide, you have the minus 0.0296, you divide by 0.277 is minus 0.096 there. Right, so as a consequence, there are going to be transformations there. There will actually be some discrepancies in the rounding off, so you'd have to sort of forgive that. And it can always be tolerated. So this one is 0.6, we've seen on the calculator. Right. And then if you have this one, need to test this one. Which is a 0.0296. 0.2777. Yeah, which is this. Minus 0.1067. Minus 0.1067, approximately. So that's correct. And then now we're going to do the next iteration. Right, and iterate, and we need to obviously iterate 3 times. So let us do another one. So to do another one, we're going to take this one and say multiplied by the same inverse. So we're going to take, for example, the matrix we got, which is 1 out of 18 minus 1 out of 3. Right. 1 out of 15. 4 out of 45. 1 out of 600. And then you multiply by this vector, the 1 minus 0.1067, and then the 0.66, etc. You multiply by it. So performing the multiplication is 1 minus 0.1067. And then you have 0.6123. Right, so when you multiply, let us perform the multiplication together. And we just check everything using our calculator. Right, we're really going to be relatively fast. Okay, we're going to quickly take, for instance, this 11 out of 18 by 1. 11 out of 18 by 1 is just 11 divided by 18. So that one we know very well. We continue with the next multiplication, this by 0, and then you would have minus. Right, minus, then you have 0.6. Right, 0.600 divided by 3, like so. And upon simplification, we have 0.41 recurring. Yeah, 0.41 recurring. So in other words, this one here is going to be exactly 0.4111. Right. So now we have, therefore, the 5 divided by 27. Right, plus. Okay, so it's going to be minus 0.067. Right, so 0.6 times divided by 45, which is now we're getting minus 0.138. Yeah, so minus 0.1390. Minus 0.1390. And then now we're going to do the 1 out of 6. So obviously 1 out of 6, because it's this by this, 1 out of 6, and then 0 by 0. So it's going to be 1 out of 6. Right. And then if we do the 1 out of 6 quickly, it's going to be 1 out of 6, and then we have 0.1667, so which is 0.1667. Okay, we are dealing with the most dominant. So the most dominant is the 0.411. 1. And then you divide these by 0.411. Right, so which is 0.1390, which is 0.4111. So which is 0.338, but it's negative 0.3380. In the same way, dealing with the other one, it's going to be 0.4054, is one can just check this out. And to check this out, I said ready to confirm this using our calculator. Then you're going to have, for instance, the note pointer. You're going to have exactly the note pointer 1667. We divide by note pointer 4123, which is note pointer 4054. Right. So now, any two iterations we obtain. So we obtain 1 over lambda 3 plus 6. Okay, so we'll therefore remember that we have just written out the following. The following. 11 out of 18. 0 minus 1 out of 3. Minus 5 out of 27. 1 out of 15. 4 out of 45. 0, 0. Right, so we have the following. And this is exactly 0.4111. 1 minus 0.1390. 0.1667. We have seen that if you extract the 0.4111, because it's the biggest one of these in magnitude terms, if you take the absolute value of that, it becomes 1. We've seen it, minus 0.3380. We saw that before, previously, and then 0.4054 that we have seen as well. When we factorize this, dividing by each of these, the largest magnitude number. And with this mentioned, we actually noted that after any 2 iterations, we obtain the following. Right, so you would have lambda 3 plus 6, 1 over. So lambda 1 over lambda 3 plus 6 becomes the same as what? After any 2 iterations. Right, so after these 2 iterations, or iterations, lambda 1 over lambda 3 plus 6 is going to be exactly this one, which is 0.4111. But also you deal with the lambda 3. Okay, if this is the case, what then is the lambda 3? We take the inverse of this. If you take the inverse of this, which is 1 over 0.411 minus 6. Right, so four one one. So now there's 1 out of 0.4123 minus 6. So now 5676. This will be approximately minus 3.5676. Okay, that is lambda 3. So we subtracted the 6 already. So this gives us lambda 3. Okay. And this is close to minus 4. So we have done so well. And now, because of this, it therefore means the eigenvector. Bring it here. So X, you'd have 1. The eigenvector is this one, and then you pick this one, minus 0.3380. And then you have the last one, 0.4054. Okay. And then we continue to then say, this was like after 2 iterations. Then we can perform 10. Okay, obviously we're not going to perform 10 now because now the method is clear. But what we're going to do is to indicate and then say, after 10 iterations, because you can just go on in the same way, but in the exam, they can't expect you to do 1,000,000 iterations to multiply like that. You're going to be tired, etc. But you don't have one question to do. You have the whole question paper. So after 10 iterations, we obtain lambda 3. 0, 0. So if you do this, 1 divided by 0.5 is 1 divided by half, which is 2 minus 6. 2 minus 6 is a minus 4.000. After 10 iterations, you're going to get this, like we've done. But it means the eigenvector associated with this would therefore become the following. X by the bottom is 1, 0.3590, 0.3333, like that. Right. So this is good news. So compare with the result, this with Right. With the results. Compare these with the result. In A, when lambda equals -4, and okay, we did this last time, and m equals 1/3. So that one was that, we're going to just bring that one to your attention. So what we have here becomes the following. So we then said for lambda equals -4, right. So for lambda equals -4, which is the 3m minus 14/13m m. Okay, this was the case. But now if we then say our m is 1/3, it means therefore the x bar is going to be 3, then 1/3 here. Wherever m appears in this vector, we're going to put 1/3 and then 1/3. Okay, yeah. Okay, we analyze this together. And if we do, what we're then getting here is these 3 cancels, giving us a 1. And then we would have if -14 out of let us see exactly if it is exactly the case. You put a minus or a plus there. Okay, just 1 second. Need to check the sign here. Is it minus, minus, plus? Okay, let us see this one here. So it is obviously a minus. And so this, let me check. Yeah, so this is also a minus after any 2 iterations. So it's going to be minus there. And so also this would be actually then a minus. Okay, just a side issue I just need to clarify. So you would have that, but yeah, this would have to be negative. Right, it would have to be negative. Let me do it in red ink. So it would have to be negative. So you have -14 out of 39. 1 out of 3. Okay. So now, using a calculator, this is 1 together with the negative. Okay, we're gonna check this one, but it appears that it's gonna be minus 0.3590, and then the other one is gonna be 0.33333. Okay, let us check -14 out of 39 using a scientific calculator and see what we get. So we're going to use this calculator to check the results. So now if we're going to say 14 divided by 39, which is 0.3590, which is this. Now with this then, obviously it compares with the 10, very closely with the 10 iterations. After 10 iterations, we get these entities actually very much the same. as when m equals 1/3, meaning that would have obtained the result there. Let us continue with the next question. Right. So in continuing with the next question, we want to investigate the following. We want to investigate the following. Right. So we will continue to investigate one of these problems very quickly. But the problem that we have mastered without any shadow of doubt, that is going to be in the, that always appears. But we have a couple of things to take note of as we um, master these to the highest level, but to every possible dimension of setting. The question becomes, what do we do if a question comes like this? With the Chebyshev polynomials and economizing series. Right. So, right. We continue. Okay, yeah, we continue with this now very fast. So, what do we have here? Now, there are certain things that you need to take into account, and they're the following things. Let us focus on this particular problem here. Given the truncated power series, this one, how is it truncated? It is truncated because it doesn't run to the power series, normally need to run to infinity. And this one has been truncated, it has been terminated. So it doesn't run to plus dot 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 dot. So it has been stopped, truncated. And the Chebyshev polynomial, this one, so we have a Chebyshev polynomial, which is t sub 5, etc. of x, which is 16x to the 5th power, and so on and so forth. What is the purpose of economizing a power series? Why should we economize a power series? Why? Why? We need words. Why should we economize a power series? In the Pade approximation method, we've mastered so much, but what is the reason for economizing a power series? So we note that an economized, right, we note that an economized power series gives almost the same accuracy almost the same accuracy as the original one. Is the original one with fewer terms. An economized power series gives almost the same accuracy as the original one with fewer terms. As the original one with fewer terms. An economized power series gives almost the same accuracy as the original series, or as the original one with fewer terms. So, as the original one with fewer terms, the economized one has fewer terms, and therefore it is able to simplify computations for us because you're dealing with fewer terms. We're dealing with fewer terms. Second Roman figure. Still given the truncated power series here, together with the Chebyshev polynomial t sub 5, economize the power series p of x. Let's economize this one. So at this point, we take note of the following. That in the second Roman figure, we have been given the truncated power series. which is P of X, which is 1 minus X squared over 2, X cubed over 3, X to the fourth power over 4, X to the fifth power over 5. The economized. The economized. Right, the economized. The economized power series is, right, so the economized power series becomes exactly what? If we take the polynomial P of X, which is this one, which is the truncated power series, terminated, doesn't run to infinity, doesn't have the plus ellipses and so on. So we have this power series, and then we subtract. We want to remove the highest power. What is the highest power here? It is x to the fifth power. So we want to remove the x to the fifth power. And here we identify x to the fifth power in the t sub 5. To economize the power series is to use elimination to remove the highest power, x to the fifth power. And if we do that, we're going to then have this x to the fifth power, and then we have x to the fifth power that occurs exactly here at this particular point. And we need to add, because this x to the power 5 is minus, and then we need to add with this one so that it can become 0. So in the end, the coefficient of x to the fifth power here is what? In the P of X is minus 1 over 5. We need to make it 1 over 5. But it is a 16, so we're going to make it 1 over 5 by 16. Because if you multiply by the 16, it's going to be 1/5. T sub 5. So now in the end, we have the following. P of X. 2. 3. 5. 16. The T sub 5. So this one plus x to the fourth power minus x to the fifth power of 5, and then we multiply everything with this. 16 is going to cancel, giving us 1/5 x to the power 5. This is 5 by 16 is 80. 20 divided by 80 is 4. Minus 1 over 4 x cubed. The 5 cancels, giving us x out of 16. So it is what? The x to the fifth power is this one is x to the fifth power. So there's x to the fifth power, and then there's x to the fifth power. So we eliminated x to the fifth power. By dint of this, we have the following assertion to make. P of x minus plus 1 over 6, 5 by that, T5x. So you have a 1 minus. Now we're going to have the linear term. So this one is going to be minus 16 over 16, which is going to be minus 15 out of 16. X. We are done with this. X squared out of 2. All right. And so what else? the x cubed. There are two x cubed. So this one, you take the LCD 12. It's going to be minus 3 minus 4 minus 7 x cubed out of 12. And then plus x to the power 4. Okay, so this is exactly the thing. Yeah, so that is what we have. That is what we have. So we continue. We continue. So which means that at this point, the economized power series becomes the following. Let's write it clearly here. So the economized power series becomes P of x plus 1 over 5 times 16 T5x. 15 out of 16 x, which is minus 7 out of 2x cubed. Right, so this is exactly what we are getting the economized power series as. This is the economized power series. So this one here is the economized power series. Right, economized, yeah. Economized power series, but it is the economized truncated power series. It's the economized power series truncated version. Next question. I want us to look at the next one. But you see, in the next case, we're saying what is the maximum value of the modulus of the Chebyshev polynomial? What is the maximum value of the modulus of the t sub 5 of x in the interval minus 1, 1? So to find this, we want to find the maximum value of the modulus of t5 of x. So now at this point, what is then the modulus? The modulus therefore becomes the maximum. So it is 16x to the 5th power, x cubed plus 5x. So what then is the maximum? Right, if you substitute everything into this, you therefore have to obtain the following. Right, so if you substitute this, so there is minus 1 to 1. If you substitute 1, what you get? You get 16 minus 20, which is a minus 4 plus 5, which gives us exactly a 1. But if you put minus 1, it's going to be minus 16 plus 20 minus 5, which is exactly minus 21 plus this. So either way, we're getting a 1. You're getting a 1 because if x is 1, you'd have 16, 1 to the 5th power minus 21, you cube it, plus 5 by 1. Okay, so it's 16 minus 20 plus 5. 21 minus 20, which is 1. Right. So if x is minus 1, minus 20 plus 5 Minus 16 plus 20, minus 5. Minus 21 plus 20, which is minus 1. Okay? But if you take the modulus of this, okay, then you do this and then you take the modulus. Modulus, modulus, modulus. And then the modulus of minus 1 becomes a 1. So also here you take the modulus, modulus, modulus. And therefore the result becomes what? The result becomes 1. So that is what we are having. And then the result becomes a 1. The result becomes a 1. So now we have the following. Okay. So the maximum value becomes a 1. Because if you take the value, because this is the minus 1 to 1 is equivalent to really saying minus 1 this. So there are numbers that are between minus 1 and 1 inclusive, 0. If you put 0, then everything is going to be 0. So and then 0 is not the maximum because 1 can be reached. Okay. So now as a consequence we would get to exactly the following. Would get exactly the following. In the fourth Roman figure, okay, if Q of X denotes the economized series obtained in the second Roman figure, what is the maximum value of the difference of these in the interval? So Q of X denotes the economized series. We have found the economized series, but we're calling it Q of X. Obtained in the second Roman figure, what is the maximum value of these in the interval? Right, would remember that our Q of X is the same as P of X minus 1 over 5 by 16 T5X, which is P of X minus 1 out of 80. Okay, we've economized it already. And then we put a plus, just a plus here. And then we have T5X. And then we're able to obtain the answer, obviously, of the economized version. And then we continue to then say, therefore, the modulus. Yeah. We then say, what is the maximum value of these? Because Q of X is the economized one. What is the maximum value of the P minus Q? Right. So we need to find P minus Q. P minus Q. So we find P of X minus Q of X. What is the maximum value? What is P of X? P of X is exactly what? And then now we have P minus Q. And so P minus Q is the same as what, according to this? Okay, so we evaluate this. So this red equation can be written as P of X minus Q of X. So P of X minus Q of X is, so yeah, P of X minus Q of X is minus 180 T5 of X. T5 of X. Right, so which is less or equal to, but first equal to. But first, this equals 1 out of 80. The modulus of T sub 5 of X. This is less or equal to 1 out of 80. And this is a decimal, can be computed as follows. So you're going to have, check this out. If you're going to do 1 divided by 80, 5 by 60 is 80 in the denominator. Okay, 1 out of 80 as a decimal is 0.0125, 0.0125, 0.0125, 0.0125. This is the case when it is certainly the case when 1 lies between those two inclusive. When -1 is less equal to x less equal to 1. Okay, so this power series, the truncated power series, would have been economized, but we're asking the question, what is it? Because we know that the maximum value of T5, in other words, T5 of x, we've already seen, its maximum value is 1. So in other words, it has an upper bound of 1, so that we have a 1 there. As a consequence, then this becomes exactly the result. Okay, take note of this. So what is the maximum value of the difference between the two functions in the interval -1 to 1, and therefore we can see it's 0.0125. Okay. Let's look at B1. B Roman figure 1. Okay. Pade approximation still being analyzed. Right, so we're looking at B Roman figure 1. We want to find the Pade approximation R6 of x with denominator of degree 3 to the function this. Okay, why is it often preferred to approximate a function by rational function rather than by a polynomial? This is the question. Why is it often preferred to approximate a function by a rational function rather than a polynomial? So we want to approximate a function, but we prefer to use a rational function rather than a polynomial. Why is that the case? Why is a rational function more preferable? We give the necessary justification as follows. We give the necessary justification as follows. We say a rational function, why is it? Okay, these questions, please, are repeating, so expect to see them. A rational approximation, right? A rational approximation can give greater accuracy, right? Greater accuracy, or essentially much greater accuracy for the same number, right? For the same, right? For the same number, for the same number of coefficients, for the same number of coefficients, or the same accuracy, or the same accuracy with fewer coefficients, with fewer coefficients. With fewer coefficients. A rational approximation can give greater accuracy for the same number of coefficients. Greater accuracy for the same number of coefficients, or the same accuracy with fewer coefficients. This gives advantage and the reason for the preference of what we call a rational function rather than a polynomial. A rational approximation can give greater accuracy for the same number of coefficients, or the same accuracy with fewer coefficients. Okay, so here we proceed. B2, B2, B2. Okay, write down R6 of x with coefficients AI, BI. So we need to write down R6. And because in Roman figure 2, we want to find a Pade approximation R6 of x with a denominator of degree 3 to the function e to the power x squared, 1 plus x squared, plus x to the 4th over 2, plus x to the 6th out of 6. Write down R sub 6 of x with the coefficients a, I, b, I. Write down R sub 6. So which means, therefore, R sub 6 of x is exactly the same as a naught, a1x plus a2x squared plus a3x cubed, all divided by 1 plus b1x, b2x squared, b3x cubed. Okay, because it's degree 3, 3 plus 3, 3 plus 3 equals 6. Okay, by dint of this, then we have the assurance. 3 plus 3 equals 6. And by dint of this, we have the assurance that it is R6 of x with those coefficients. Degree 6. Degree 6 of the rational function. Of the rational right of the rational approximation. According to rational approximation. Okay, now we move on to the next point. Let's look at B3. Okay, I want us to discuss B3 right now and conclude our discussion and see if we can do anything next. Okay, let's look at B3. B3. Okay, Roman figure 3, still focusing on the Pade approximation method and looking how it can be used. Set up. This is the instruction. Set up the equations to find the coefficients, but do not solve the equation or do not solve the system. But do not solve the system. But what are you supposed to do? Just set up the equations to find the coefficients. That's all. And that's all. Then you're done. E to the power x squared minus R6 of x. Okay, now we have to actually look at this here and realize that if we have e to the power x squared still minus R6 of x. What is this? What exactly is this? So at this point, you'd have exactly the following to deal with. So you have the e to the x squared, which is 1 plus x squared plus x to the 4th power out of 2 plus x to the 6th power out of 6, and so on and so forth. And so on and so forth. So this becomes the, well, in particular, this becomes what we call the Maclaurin series. Maclaurin. Right, Maclaurin series of the e to the x squared. But this is in line with the fact that the Maclaurin series of e to the power x is 1 plus this. And then we have exactly x squared over, right, then you have x squared over 2. Okay, normally we write 2 factorial. And then we write x cubed over 3 factorial, right? And this pattern continues. But what is R6? What is R6? Right. What is R6? So we continue to check our R6. And now, what exactly is our R6 here? Okay, our R6 here, because we're dealing with the polynomial, so our R6 is going to be given by what? It's going to be, yeah, okay, we have created it because it's R6, so it's going to be A naught, A1x plus, right, A1x plus A2x squared plus A3x cubed. We divide everything by 1 plus B1x plus B2x squared plus B3x cubed, and so on and so forth. Okay, so in which case, therefore, this is being subtracted. So we actually need to put a minus because it is e to the power x squared, the polynomial, minus the exponential minus the rational approximation. Now, if you add everything, let us start from the margin to actually economize on space. And beginning from the margin, we have this, we need to add with this, subtract everything together. And by dint of that, then you'd have 1 plus x squared plus x to the fourth power over 2x to the sixth power out of 6. Okay, we will go on with this, and then it is multiplied by the following. Right, so you have 1 plus b1x, b2x squared, b3x cubed, and so on, minus. Okay, so instead of cross multiplying, this multiplies that. And you're going to have, therefore, 1 that multiplies the a, this a's here. So you have a naught, a1x, a2x squared. This is a 2. And then you have a3x cubed. Like so. All this is therefore divided by the 1 plus b1x plus b2x squared plus b3x cubed. Like this. So now we have this numerator. So now what we do is that if this is the right approximation, then the numerator must become 0. In other words, we're going to make this equal to 0. And we're going to write exactly the following. We're going to have 1 plus x squared, x to the fourth power over 2, and then x to the sixth power over 6, which is 1 plus b1. b2x squared, b3. Right. Which is a naught, a1x, a2x squared, plus a3x cubed. So this numerator, you're going to equate it to 0. In the numerator, so in the numerator, set the coefficients. Set the coefficients of terms 1x and so on up to x to the sixth power equal to 0. Right, equal to 0. And by dint of that, you're going to be able to have the following. For 1 minus a naught is 0. X. B1 minus A1 is 0. For x squared, B2 plus 1 minus A2 is 0. x cubed. B3 plus B1 minus A3 is 0. X to the fourth power is going to be B2. Okay, we're going to discuss why this is the case. Because we need to just visualize the multiplication. And then B3 plus a half B1 is 0. X to the sixth power is going to be half B2 plus 1 out of 6 equals 0. So now in the end, you have exactly 1. 1 by 1 is 1 minus A naught. That is why the constant is 1 minus A naught. It becomes 0. And then the next one you're going to check is the X term. So the X term is going to occur when you multiply by what? For example, when you multiply 1 and B1. So there's going to be a B1 there, but also there's going to be minus A1. So there's B1 minus A1, which is going to be 0. And this pattern continues with the multiplication here, and you are able to get this. So set up the equations, but do not solve the system. So because there are lots of them, they said do not solve the system, but these will become the equations in the case of the Pade approximation technique. Right, so we're going to have this, but we don't need to solve anything. We don't need to solve any single thing. But because we are dealing with R6, the degree that we're dealing with, obviously, it's sort of the highest degree 6. The highest degree 6 there. Right. And I think that it was awesome having this discussion. And there are a lot of things we shall discuss in our next meeting. And we shall obviously communicate that to you when we meet at the time, according to the scheduled time slot. And then we shall look at the other things that are still outstanding, and we shall see, obviously, how well we do because we have right. Okay. Right. Now, yeah, I was saying, therefore, we're gonna share the other things. The other things we're going to discuss. The other things we're going to discuss in our next meeting. And so we're going to meet again on Friday. Yeah, on Friday. Yes, on Friday, the 4th of October. Right. At the same time, 10 a.m., then we should be. Yes, correct. Yeah, so obviously, see, our discussion is recorded because we know the network can fail sometimes during the course of the discussion, but the recording will always have um, sound that is consistent because the recording is happening at the source. It's happening at the source of the sound and the visuals. So there cannot be any loss of sound or visuals or anything like that. So we shall send the recording in the next couple of minutes. But thank you so much for joining us. We shall share the recording as we prepare for the assessment that is on the way in a few days for this module. Okay. Right. Thanks a lot, dear. Until Friday, we keep in touch on WhatsApp. We'll keep you posted with the recording and any information that will arise. But thank you so much again. Take care and have a good day and God bless. Okay.
Bye.
Thanks. Goodbye. Goodbye.